Hello everyone and welcome to this exciting video where we will discuss about solid principles, the fundamental principles of object-oriented design. In this video we will dive into the 5 essential guidelines that help us to write maintainable, scalable and efficient code. The solid principles were introduced by Robert C. Martin in the early 2000s as a set of guidelines to create cleaner and more scalable software. They have become widely adopted in the programming world, making them essential for any developer's toolkit. Those principles are single responsibility principle, open close principle, Liskov Substitution Principle, Interface Segregation Principle, and Dependency Inversion Principle. Here we have Mr. Aita with us, who will be our guide to understanding these principles with some real-world examples. Let's get started. The first one of the solid principles is the Single Responsibility Principle or SRP. This principle is all about keeping things simple and focused. Once upon a time, our friend Mr. Aita got a job. At first, he was super excited to develop a brand new application. But as time went on, the management also asked him to test it and take care of the company's security. It was a lot for just one person to handle, and Aita felt overwhelmed. Thankfully, Aita was a wise developer and he knew about the single responsibility principle. He decided to discuss his struggles with the management and they listened. So they hired another skilled person to take care of testing and yet another expert to handle security aspects. That's how the single responsibility principle saved the day. Aita's story teaches us the importance of keeping each person or class responsible for just one thing, making everyone's work easier and the code cleaner. Alright, let's dive into a real world example of how we can apply the single responsibility principle in code. Here we have a class that's supposed to do just one thing, calculate the mean of some numbers. However, it does not follow the SRP. It's like wearing multiple hats. This class is doing more than just calculating the mean. It's also handling data type parsing, making it messy and confusing. In other words, it has two reasons to change this class, parsing and the computation. To make things right, we will apply the SRP. We will keep only relevant actions that match for the mean calculation and we have removed all the codes for parsing. This way, it's much clearer and concise. Yes, of course, we need to create a separate class, one for the handle data type parsing. We will discuss it later during the next steps. Let's move to the second principle now, the open-close principle. Let's follow our friend Mr. Aita on his laptop adventure to understand this principle better. Mr. Aita is super excited to buy a new laptop. He finds a fantastic laptop and buy it. But wait, he's already thinking ahead. He knows he might want to enhance it later with a bigger monitor, a gaming keyboard, a fancy mouse and a powerful speaker. Now here is the cool part about the open-close principle. Mr. Aita's laptop is already closed for changes. It's a complete functioning laptop, but it's open for extension. He can add those extra goodies without altering the laptop itself. Just like that, in our code, when we design classes, we want them to be closed for modification, so we don't mess up the existing code. But at the same time, we want them open for extension, so we can add new features or enhancements without changing the original class. Let's see how this works in code. Let's create a parser for the above calculator application. Note that this will be passed given CSV data only at the moment. So we have the parse method which will accept a string parameter and split it. Then in the toDoubleList method, the given string array will be converted to a double list. After some time, the requirements have expanded and now the app needs to support parsing XML data too. We can make changes like this by introducing a new method to parse the XML and call it in our parse method. Yes, obviously, this will break the single responsibility principle. Then what will be the better approach? So we can decide to tackle this issue using an abstract class, which is a powerful concept in the world of object-oriented programming. We can make the split method abstract and do the implementation on separate classes based on the input type. Like this, we can introduce two new classes for parsing CSV and XML data separately. Note that we are not doing modification for the new requirement by violating the open-close principle. We are trying to adapt the solid principles to face upcoming new requirements. The third principle is the Liskov Substitution Principle. Mr. Aita is an animal lover and he starts his journey by getting a cute little cat named Whiskers. He loves spending the time with Whiskers, cuddling and playing with her. Now Mr. Aita decides to add more joy into his life by getting a puppy named Max. But here is where the LSP coming into play. The Liskov substitution principle states that objects of a superclass should be replaceable with objects of its subclasses without affecting the correctness of the program. Whiskers and Max may have different behaviors and characteristics, but they both bring joy to Mr. Aita's life as pets, and he can love and care for them in a consistent way. Now let's see the LSP in action with the code example involving our parser class, the superclass and its subclasses CSV parser and XML parser. As we have learned, LSP states that objects of a superclass should be replaceable with objects of its subclasses without affecting the correctness of the program. In our code, the superclass define a common method called split CSV parser and the XML parser subclasses inherit from the parser superclass, and they both implement their own version of split methods to handle the specific data types. The beauty of LSP is that we can seamlessly replace the parser superclass with any of its subclasses. They all adhere to the same contact of split method, so our code works smoothly without any unexpected behaviors. Next, we will explore the Interface Segregation Principle. Mr. Aita loves his gadgets and has a TV, a radio, and a DVD player. He thought it would be fantastic to have one remote control that can operate all three devices and all in one remote. However, this idea hits a roadblock when Mr. Aita learns about the Interface Segregation Principle. The Interface Segregation Principle states that a class should not be forced to implement methods it doesn't use. In our case, this means that each device should have its specific remote control with only the buttons it needs. Realizing this, Mr. Aita takes the right approach. He decides to get three separate remotes, one for the radio, one for the TV, and another one for the DVD player. Each remote is tailored to the specific needs of the device it operates. Take a look at this authorization service interface. We notice that it contains too many methods, and some implementing classes may not need to use all of them. Remember, the ISP advises that a class should not be forced to implement methods it doesn't use. In our code, this means we should create more focused interfaces to cater to the specific needs of the implementing classes. To resolve this issue and follow the ISP, we can take a simple yet powerful approach. Let's refactor the authorization service interface into two separate interfaces. By splitting the authorization service into the two interfaces, we provide more focused contracts for the implementing classes. Now each class can choose the interface that align with its specific needs, preventing unnecessary method implementation. The final solid principle is the Dependency Inversion Principle. Our Mr. Aita has a modern mobile phone and it is a complex device with many internal components, circuits and functionalities. But here is the interesting part. It only exposes a few things to the outside world. The Dependency Inversion Principle tells us to depend on the abstractions, not concretions. So the mobile phone exposes a few essential abstractions like the power button, the volume button, charging input and so on. These abstractions act as a high-level modules that hide the underlying complexity. By adhering to the DIP, the mobile phone becomes more flexible and adaptable. The internal components can change or improve without affecting the exposed functionalities. As we have learned, the DIP encourages us to depend on abstraction, not concretions. Here we achieve that through the power of interfaces. We create the iParser interface, defining the high-level behavior for all parsers. It's like a contract that any parser class should adhere to. Next, we have the parser class, which implements the iParser interface. By doing so, it must provide an implementation for the parse method as defined in the interface. Now with the DIP in action, any class that interacts with our parser doesn't need to know about specific details of the parser class. Instead, they depend on the high-level abstraction provided by the iParser interface. We have reached the end of our journey through the solid principle. Let's take a quick recap. SRP keep classes focused on one job, like having experts who excel in their specific roles. SRP ensures that classes have a single reason to change, making our code organized and easier to understand. OCP indicates that the code should be open for extension but closed for the modification. By using abstraction and interfaces, we can add new features without altering existing code, promoting code reuse and adaptability. With the LSP, we have discussed subclasses should be replaceable for their superclasses. When a subclass adheres to the contract of its superclass, it can seamlessly replace it, making our code flexible and scalable. ISP guides us on how classes should not be forced to implement interfaces they don't need. By creating focused interfaces for specific behaviors, we avoid unnecessary burdens and achieve cleaner, more maintainable code. Finally, DIP forces us to depend on abstraction, not concretions. By using interfaces and abstract classes, we create high-level modules that hide internal complexities, promoting loose coupling and future-proof designs. As we conclude our video, let's remember that the solid principles are not strict rules, but rather guidelines that help us to craft top-notch softwares. Thank you for joining me on this coding adventure. Now let's go out there and build amazing software that showcases the magic of solid principles. Happy coding, folks!